Section 2.7 talks about combining functions, and here we start off with the algebra of functions, and that is, if f and g are two functions, then if I'm adding the two functions, subtracting works straightforward, multiplying and dividing works out identically, provided the denominator doesn't equal 0. So it's pretty much what you see, not that challenging. But if I'm talking about a domain, it turns out those three have the same domain. The only difference, this will be the same with the exception of the denominator not equaling to 0. So let's play with that, see how that goes. If I run the first equation, example A, find f plus g, f minus g, f times g, and f divided by g. Well, it's fairly simple because it's pretty much what you see. If I take f plus g operating on x, well, by definition, that's f of x plus g of x. F of x is 2x plus 1. G of x is radical x. Now, the fact that radical x has a domain of x has to be bigger than or equal to 0. The fact that I see that right there, automatically I know that that already applies, and my answer will be 2x plus 1 plus radical x. That's pretty much it. What's the domain? Well, it is x is bigger than or equal to 0. So 0 to infinity, done deal. When I say, let's find f minus g of x, well, it's no big secret. It's pretty much the same thing. F of x minus g of x, that's simply 2x plus 1 minus radical x. There it is, done. What's the domain? It's right there. It's identical. It doesn't change. So the domain, once you find the domain for one of those, you find it for all of them. When I go for f times g operating on x, that is f of x times g of x. Well, f of x is 2x plus 1, and g of x is radical x. There it is. Domain identical. Right there. Domain 0 to infinity. And if I go by the division, now things will change slightly. F divided by g of x would be f of x divided by g of x. So the domain is the same, but I need to add the condition that the denominator cannot equal 0. So you see how here it's included. All of these have 0 to infinity as domain. This would be 0 to infinity. Add to that, x cannot be 0, meaning what? The only difference, I wouldn't include the 0. And that's pretty much it. So, adding, subtracting, multiplying, dividing, turns out to be pretty much the same. Here, if I go for f plus g, so this is the next example. If I take f plus g of x, well, that is f of x plus g of x. I'll talk about the domain in a minute. And if I want f minus g of x, well, that is f of x minus g of x. No difference. If I take f times g, well, that's simply the square root of x squared minus 4 times the square root of 9 minus x squared. And if I take f divided by g, that's nothing more than the square root of x squared minus 4 over the square root of 9 minus x squared. Now let me elaborate really quick. If I look at f, domain, I want x squared minus 4 to be bigger than or equal to 0. And if you remember from a graph, you could make a table, a list of table like we did on exam 1. Do you remember that? Or you could say, well, but wait, now I know how to graph. This is a graph of a parabola shifted down 4 units. Where is this bigger than 0? Negative infinity to negative 2 union with 2 all the way to infinity. That's the domain of that piece. When I say what's the domain of this piece, you say, well, 9 minus x squared must be bigger than or equal to 0. Well, you say, wait, but I could make a table, or I could say that's an upside down parabola shifted up 9 units. Negative 3 and positive 3. Where is that bigger than or equal to 0? From negative 3 all the way to 3. And anytime you have multiple domains, you look for overlap. Do you see that overlap is the overlap here is negative 3 to negative 2 union with 2 to 3. And that's going to be the domain for this, for this, for this. The only exception on the last one is when we look at it, we notice that the denominator is really this. We can't have that equal 0. So where does that equal 0? At 3 and negative 3. So the only exception, the domain for the last would be parentheses negative 3 to negative 2 union with 2 to 3 not including. But the domain for each of those, this piece, and this piece is identical to that. And that's how this works. Now, composition is a slightly different game. A bit annoying in the beginning, but we'll get the hang of this. I see what's happening. That's how we normally do it. Okay. So if I look at what a composition is, given f and g are functions, the composition f of g of x, or f composite g of x, it's kind of like g of x, and you take f of that. So if I want to deal with f of g of 1, so this is nothing more than y values, a bunch of y values. If x equal 1, what does y equal? Well, which y? This y or this y? Since that says g, it's this y. If I put a 1 in there and a 1 in there, isn't that 1 minus 3 plus 2? Isn't that a 0? And now what is this saying? This says what does y equal when x equals 0, but in which y? This function. If I put a 0 there for x, wouldn't you get 2 times 0 plus 1, which is 1? And that's pretty much it. So nothing more than evaluating some y values. How about here? This is g. What is y equal when x equal 1 in this y? If I put a 1 right there, 2 plus 1 is 3. And now what is this saying? Tell me what y equal when x equal 3 in this equation. That will be 9 minus 9 plus 2. That would be a 2. So f composite g of 1 and g composite f of 1 are definitely not the same. Sometimes they are, but most of the time they're not. And what is this asking for? This says find g of 0. So don't let that throw you off. That is, what are the y values? If x equals 0, which y? This y or this y? Well, obviously this. If I put a 0 in there, I'll get 0 squared, which is 0 minus 3 times 0 plus 2, that's a 2. And now what does this say? This says go back to the same function and now find me the y value when x equal a 2. If I put a 2 right there, that will be a 4 minus 6 plus 2. That happens to be a 0. Just a coincidence, you guys. And what if I wanted f of g of x? Well, what does y equal? According to g, y is right there. That's what y equals. It's all of this mess. And what is this saying now? This says go and find me the new y, but in f here. How do you find y? Well, you replace x by all of this. The 2 you copy down, replace x by all of this mess, clean it up, and you're done. And there's a plus 1. So that would be a 4x squared minus 6x plus 4 plus 1 is a 5. And what if I wanted to find the G composite f of x? Same thing. No, it's not. Every now and then it is the same. The majority of the time it's not. So again, you're finding a bunch of y values. This says find me the y value. Well, which y? The inside. Y equal to x plus 1. Find me another y value. Wherever you see an x in this g function, throw in that mess. Well, I'm going to throw in that mess and square it. And there's a plus 2. And clean that up and I'm done. 4x squared plus 4x plus 1 minus 6x minus 3 plus 2. That would be 4x squared minus 2x. 2 plus 1 is 3 minus 3 is 0. And there it is. So finding a bunch of y values, that takes some practice. I'm not going to dare and move that. So how about here? Well, the same deal. This is f. What does y equal when x equals 0? Which y? The g, the blue. If x equals 0, isn't the y 2? And now what is this saying? This says go to f. F is the red. If x equal 2, what does y equal? Isn't that a 1? So it's kind of like a puzzle, but you're always looking for the y values. Always. You rarely look for the x. X is given, find y for me. And if I go to the next problem, part B, well, this is g of, go into the f. If x equals 0 on the red, what does y equal? Isn't that a negative 2? And now this says go to the blue. If x equal negative 2, what does y equal? So it's always y values. And if I run, find f of 4. Again, don't let that throw you off. If x equal 4, using the red. If x equal 4, 1, 2, 3, 4. What does y equal? Well, that's a 0. But this is go back to f again, the red. If x equals 0, what does y equal? A negative 2. And here we're just going by the blue. We're not going to use the red for anything. And that is g of, if x equal negative 4, 1, 2, 3, 4, negative 4, isn't y negative 1? And when it says, if x equal negative 1, what does y equal? Well, that looks like a 3. Oh. So I messed up on this piece. This is negative 2, 1, 2. Oh yeah, that's not 3. That's a bit below 3, right? Yeah, okay. So what does that look like? That looks like 2.8, 2.9. We're not going to disagree. Whatever you think that is, as long as it's close to 3, will be fine. And what if they gave me a table? So this is the same thing given a graph, given equation, given points. Kind of like we did with functions. What is this? Well, this is f of, and let me give me 1 sec. Give some space. Okay, and mind if I notice what this says? Well, y values. If x equals 0, there is no x equals 0 anywhere on this. Do you see that? So automatically this is undefined based on the table. Okay, how about this problem? If x equal 2, there's x equal 2. What's the y value? Which y value? This y value or this y value? Well, it says x, f of x, so that's a 5. And now what? This says when x equal 5, there's x equal 5. What does y equal? Which y? Well, the g. Isn't that a 2? Okay, and how about here? This is f of 3. Again, a bunch of y values. If x equal 3, I forgot about that. I made this up. I didn't copy it, so I can't just erase all the lines. So now we're going to start the game over. If x equal 3, what's y equal? Y equal 1. And if x equal 1, what's y equal? Which y? Always this y. It's a 4. And here, this is g of 5. This is g. If x equal 5, what's y equal? Well, we're sticking with g in this case for both cases. That's a 2. And if x equal a 2, what does g equal? That's a 4. So finding a bunch of y values, that's all what we do here.